Yeah, thank you. I think the reason that I'm here is that there was this meetup you organized with Motional, and you asked, oh, but how do you actually select the data? And that's a great question, and the answer will take 2 hours.
Sometimes I ask questions that make sense, just sometimes.
Yeah, but it's a question which is so good that the answer will take a long time. Maybe one thing I figured. So indeed, the first. So what I will try to do is first give like a theoretical talk, but I also like to try things hands-on. So already a couple of months ago, I made some Jupyter Notebooks to explain some of those concepts in a hopefully clear way. But to do that, let me just skip the entire presentation. What you can do is download this repository I have. Peter already sent the link to the chat. If you download that to a computer which supports NVIDIA Docker containers, then you can follow the README file to create a Docker image. It's just 2 commands, Docker build and Docker run. And then you have a Jupyter Notebook running locally on localhost 8888. You should see something there. If you want to scavenge your own data, or if you have your own data for the workshop, that would be awesome. If you don't have your own data, you can start by getting an API key for Mapillary, which is basically kind of Google Street View. And then you can open my Mapillary scrape notebook to adjust the API key and maybe adjust latitude and longitude, and you can start scraping data. Or what you can also do is download, I zipped 1,000 of these images, and you can download that as this Google Drive link. Overall, I always think that the more data you have, the better and the more fun. But at least this is 100 megabytes, which will get you started, at least for the notebooks. And the link to this data is in this presentation, which is linked in the GitHub page. So I would kind of recommend to start doing that now. If you have questions, just type them in the chat, and Peter will interrupt me because I don't think I can see the chat while I'm talking.
Yeah, I will be interrupting. You know what? Already an interrupt. Is it possible to run the code on Colab instead of our local machines?
Oh, it's a good question.
I'm trying to do this now. I just don't know if it is.
Yeah. I think it should be possible because as long as the data is in Colab, or as long as you are linking to some data in Colab, it should be fine.
Yeah, I think it's working for me. Anybody who's here, I'm gonna let you know once it's finished.
That's actually a good idea. I should have put it in Binder or Colab or something to immediately share it. I'm always just running it on some cloud machine, but that is an easier workflow. Also, Peter already said it, but if you want, you can like turn on your webcam if you want, and something is not clear, just interrupt me, and we can have a discussion, whatever. So yeah, I'm Roland Meert. I'm a product manager at Anatel. My background is in AI, artificial intelligence, and robotics and autonomous driving. So before I was a product manager at Anatel, I was a machine learning engineer at autonomous intelligent driving and Argo, building self-driving cars and machine learning algorithms for self-driving cars. And what I noticed is that the biggest problem with self-driving cars, in my opinion, right now is, or at least it was for me, is getting the right data and having the right quality of labels. So what we're going to look at today is basically, why is data selection so important for the performance of your algorithm? How can you select data before you are training any model? And I'm going to go over a couple of active learning techniques to improve your existing model. So what I want to go through is go over underrepresented labeling to find images which are likely to contain underrepresented classes. Uncertainty sampling to label things where the model is most uncertain. I want to go over query by committee, where you train multiple models and you label data where the models disagree. And at the end, I want to do something which I think is really cool, which is querying techniques to find similar data. So if you are having problems with a specific scenario, can you find similar data to the scenario? Again, if people have problems with setting up this notebook or setting up the Git or something, just type a message. I see Peter working really hard to get it into Colab. Very good. Yeah. So if you're going to like public data sets, what we see in self-driving is that before January 2018, there were already many data sets like the famous Kitty data set, the Udacity data set, the Mapillary Vistas data set, and recently in the last couple of years, there were even like data sets are just getting bigger and bigger and having more and more data. So now you also have the Waymo data set. Kitty has been expanded with new types of annotations. The Lyft data set is really big. So people are collecting more and more data. Nucines is also a really famous one, which is used a lot in autonomous driving. But the big problem with data sets and machine learning is often not the amount of data which you have, but the type of data which is in your data set. So what I looked at here, someone at Nucines made an overview of how many points there are of each type in the Nucines data set. And what you can see is that a lot of LiDAR points are hitting a drivable surface. So basically the road or man-made objects. So basically buildings or trees. And there's also many points which are hitting a car. But there are already like 10 to 100 times more points hitting cars than are hitting adults. And there are already way more points which are hitting an adult than hitting a motorcycle. And there's then another order of magnitude between a motorcycle and a bike. Bikes, by the way, are really awesome because I'm Dutch, but they are terrible for autonomous driving because they rarely occur in your data set. So you're always having a problem with recognizing bikes. And so even if you have then your bikes, then you still have specific things like a wheelchair is already harder to find in your data sets. And it's even rarer to see like a police or an ambulance vehicle, even though we as humans have are very much focused on knowing that an ambulance is coming, because then you need to perform a special action. We are very careful around animals and we are very careful around wheelchairs, but in practice in your data set, those objects occur less often. And as people probably know in machine learning, if you have an unbalanced data set, your model will kind of have issues recognizing those objects. And not only...
I have a quick question. So I know that this, the kind of general point is that, for more and more specific classes, we have less points, but is that the convention in autonomous vehicle companies, is to kind of break it down into such like fine-grained categories, or would you just lump everything and say, that's a car or that's a pedestrian?
Yeah, so the other option is basically break it down into this is a car and this is a movable object. But in practice, you're going to, or what we always had is that we like as soon as something is a bit weirder, a bit out of the normal, your problem will have a problem recognizing it. So in the end, for your validation, you still want to roughly know those rare classes because you also have to recognize them. So you can break it down into dynamic objects and not dynamic objects. And you can also have like unsupervised techniques, which just extract moving objects from the scene. But in the end, you want to have those finer grained classes to not only recognize them, but also evaluate on them. So one of the things you have to prove if you're letting your self-driving car on the road is, for example, does your car stop when there's a school bus, or does your car stop when there's a crossing child? So it's really good to explicitly have these scenarios in your scenario database so you can validate on them. So in that sense, it is, at least for validation, very useful. And then for training, it's useful to have them because then you know that you can cover them. Does it answer your question?
Yeah, it does. I like the example, that helped.
Yeah, and maybe then the other thing is not only is the present important, but the context in which an object occurs is also important. So if we're talking about a jaywalker or like a person, they are often on the side of the road, but sometimes they're crossing, right? So how often do you see a person with an animal jaywalking, or how often do you see an animal walking alone over the road? So maybe it's not only about recognizing the wheelchair on the sidewalk, which can be important, but also having these objects be in a situation which is relevant to you, which to which you have to adapt your driving behavior is really important. So overall, like the automotive term is kind of that people are setting up an operational design domain, an ODD, which is this is the list with scenarios we want to cover for our self-driving car. Like normally I go over kind of what kind of scenarios do you have to cover for your self-driving car, but now I'm just assuming everybody knows. But so if you have to cover a certain set of scenarios for your self-driving car, how well does your data cover these scenarios? If your car has to be able to drive in the rain and snow, how much data you actually have in rain and snow to be able to validate that you can do this? Same for training. If you are always training an algorithm, like everyone who works with computer vision is always annoyed by this, because you train your algorithm during the day or something, and then you try it for your demo at night, and suddenly everything looks different and doesn't work anymore. You basically want to make sure that your data covers this as well. And one thing I always like to say is that the world is always changing, and there's kind of an infinite amount of edge cases. So in terms of the world is changing, when I was working at this self-driving car company in 2019, at some point, Germany legalized e-scooters. So then from one day to another, there's kind of a new class on your road. And in terms of edge cases, we all have seen videos of a plane landing, but it's not something which is occurring in a data set. But you want to, preferably you want to make sure that your car can handle edge cases, or at least recognize that it's an edge case. And if you see something which is rare, you want to capture it. So that's where the whole edge case detection and data labeling comes in. And one thing I always think is interesting is that the human brain is really quick to adapt. So we released those e-scooters, and there were a couple of accidents, but after a week, scooters and cars and everyone was like happily driving together. But so a self-driving car should also be able to handle unknown objects. And if you have an AI fleet and you have a new kind of type of object on the road, you should be able to learn fast from new situations. Like in this case, you see a truck coming, burning truck coming down. That's rare, but humans will probably like stop and see what's happening. And self-driving cars have to quickly adapt. One thing I wanted to do is quickly show how Tesla does this, because they are always miles ahead. So that's a 3-minute video, and then I don't have to talk, but André Kapati can talk. Let me know if you don't hear the sound.
So even taking a very simple task, like for example, stop sign, you think that neural networks are capable of handling thousands of categories of ImageNet with all their variations and so on. So how difficult is it to just detect a fixed pattern of like red on white stop? And it actually gets quite difficult when you get to the long tail of it, even to create a simple detector for a stop sign. So first of all, stop signs can, of course, be in lots of variant environmental conditions. Stop signs can not just be on poles, but can just like on walls. Stop signs can be temporary and just hang out in different configurations. Stop signs can have funny lights on them, which are supposed to make it easier to see the stop sign, but for our system it's the opposite. We have to actually explicitly worry about it. Stop signs can be held by a person. That stop sign can be in an inactive state or an active state. Stop signs can be on like these cones. Stop signs can be heavily occluded in lots of ways, by foliage, by signs. Stop signs can be occluded by cars. Stop signs can be part of cars, and they can be part of cars in an active or inactive state again. Stops can be sort of held by a person. Stops come with lots of exotic modifiers to them. So this stop only applies except right turn. This stop says take your turn through this place. This stop is right turn, keep moving. So do not stop if you're going right. So there's a variety of modifiers, all of them we have to care about because they actually have impact on how you should drive through this final space. And as I mentioned, everything is AI vision based at the moment. We do have maps, of course, that we build, but they're not high definition maps. But stops can be attached to gates, but they only apply when the gate is closed. When it's open, they do not apply. Stops can be on arms. These arms can lift, and then the stop sign does not apply anymore. Stops can only apply when you're taking a left, so they're action conditional. And so basically there's a massive variety of, even just for a stop sign to get this to work. And what we do day to day in the team is we are going through the long tail and we're building all this infrastructure for sourcing all these additional examples. And so I've shown in the Autonomy Day presentation earlier last year, the data engine, the process by which we iteratively apply active learning to source examples in cases where the detector is misbehaving. And then we source examples in those and we label them and incorporate them into part of the training set. So for stop sign detection, as an example, we have a approximate detector for stop signs based on an initial seed set of data. And we run that and deploy that to cars in shadow mode. And then you can detect some kind of a lack of health of that detector in test time. So for example, the stop sign detection is flickering. That could be a source of uncertainty. You can also detect that the neural network is uncertain in a certain Bayesian way, and there's a few ways to model that. You can find instances where you get surprised to see a stop sign. Like, why didn't you see it when you were a bit further away? You can also source examples when we detect a stop sign, but the map thinks that there should be no stop sign, or vice versa. So sort of a map vision disagreement. So we have lots of different ways of sourcing difficult cases, and then we upload images and we look through them, we label some of them and incorporate them into a training set. As an example.
So yeah, that's basically what we're going to do today. Is we now know that detecting stop signs is really hard, and it's there's many ways to basically try to source additional data. So yeah. So bam, can I go to the next one? Yeah. So let's maybe get started with selecting data before training a model. So there's a couple of data selection methods, right? So the most obvious one, or the easiest one, is you just randomly select frames. You just drive for a day and you take, I don't know, every minute you take a snapshot of a camera, or maybe every 10 seconds or every second. And you just have in your data set whatever comes up in your data set. So that's a really easy way to implement, but it might not give you full coverage of all your edge cases. The other option is, if you're a self-driving car company, right, that's what you start with, because for your initial data set, it doesn't really matter what you have. Then after a while, you're probably having a problem with specific cases. So then you can get started manually selecting interesting frames. So for example, you say, oh, whenever we see a bike, we press a button, we are really happy because then we've got another bike in our data set. But this takes a long time and you don't really know what cases you missed, right? Because you know what data you have in your data set, but you don't know what, like if you would drive for 100 hours, you don't really know what you missed. Then there's the rare data selection. So you can use a trained algorithm to find likely cases of a rare event. So for example, you could build a detector which can detect bikes, and then you just take all of your unannotated data and say, oh, show me all the images where there might be a bike. Then the next thing is active learning. So active learning is really about, if you are having a trained algorithm, what data should I give to this algorithm to learn more about the underlying distribution? So what data should I give to the algorithm to improve my algorithm, to improve my neural network? So one method, for example, could be to take the cases which are giving you the highest uncertainty, because apparently that's something the network doesn't really know what to select or what to do. And then you label those. And then another thing is finding similar samples. So if you, for example, know that you have a problem with bikes or children on bikes, you can use reverse image search to find similar examples to what you're having a problem with. And then a last idea is data coverage. So if you didn't label a lot of data yet, can you find a set of data points, I don't know, 10,000 data points or something, which accurately covers your ODD, which accurately covers your entire driving space, and then you send that out. So yeah, those are the things I'm going to discuss in terms of active learning. So if you have a set of data which is labeled, the question is really what data do you select from your unlabeled data to be labeled? So here we normally already have a trained model, which we are specifically looking to improve. And there's this learner, which it could be a website or could be a car or whatever. that observes an instance and then can already make a decision. But it can also, this algorithm basically decides, do I want to query this instance? Like, do I want this instance to be labeled or not? And Oracle basically means labeling service, or the machine learning engineer who is sitting behind the laptop who has to label it himself. Or you can say, okay, well, I made a decision on this data, and even though I don't know what the label is, I believe that I don't want this to be labeled. So I have this in a Jupyter Notebook as well. There's a kind of a difference between neural networks and other machine learning techniques. So it costs time and money to set up a labeling project, and training a neural network takes time and resources. So instead of querying, like in this graph, it looks like, oh, you just take your one instance and then you query it and you prove it. But what you want to do if you're training a neural network is query a whole batch of instances, and you basically want to select your next 1,000 or 5,000 or 10,000 or 100,000 frames to be labeled, instead of sending a single instance at a time, which I'm kind of going to ignore today, but it's good to keep in mind later. So if we're talking about uncertainty sampling, the goal is to find unlabeled samples on which your current model has a large uncertainty. So for example, if you're doing Bayesian optimization and you know a couple of data points, you have a rough idea of the function, but you also know where you are really uncertain. So then the idea is that you take something in between here where you have a high uncertainty and start querying points like this. And for neural networks, you can kind of estimate uncertainty. So this is what André Kapati was talking about, right? There's some kind of interesting methods for this. So you can estimate uncertainty by leaving dropout layers. By the way, if people don't know what dropout layers are, or are missing some knowledge on like neural networks, just talk. But if you have dropout layers in your neural network, you can kind of leave them in and run the inference step multiple times. And what this does is that this gives you, for one image, so let's say that you have this input image and you are trying to do semantic segmentation. If you do that many times, you can get the average of all the predictions, and you can also get the standard deviation of your predictions per pixel. So that gives you kind of an uncertainty map, where in this case, the more black a pixel is, the higher the uncertainty is. So what you can see is that the neural network has problems detecting the edges of objects, which is pretty normal. But there's also some places where the neural network has a bit of where the uncertainty is a bit like a bigger, darker patch. So for example, what you can see here is that here the roadworks, they are like having a big dark patch here, because I guess that the neural network didn't really learn what roadworks are. Say maybe here, you see some places where there's some darker patches where you can indeed not really see what's going on. Or also here, the area around the bike is a bit more uncertain. You see it back here as well, and there's some roadwork sign, I think, here as well. Oh. But yeah,
I was just so are these? Let's say that I'm having trouble understanding if it's. Are we talking about unknown unknowns? So this is where it's never encountered a category before, or is it kind of like known unknowns? So you've already trained a little bit on a category, but you're a little bit more uncertain.
Yeah, so in this case, you trained on a set of categories. And what you do is that you run inference multiple times. And so here in this case, in the center of the car, it's really clear that it's a car, right? And the neural network is also pretty sure that even if you modify the image a bit, it still thinks it's a car. So then every time in all these pixels, the predicted class is a car. However, here, apparently the neural network has seen less roadworks or less of this type. So if you are running the algorithm multiple times on this place and always modifying the inputs or modifying the weight activations in the network, you get different predictions. So sometimes the network might predict, oh, it's a border. Sometimes it might say it's drivable. Sometimes it might say it's car. You don't know. But then the predictions differ. So as soon as you have those switching predictions, it kind of means that this is kind of a decision boundary between what the neural network thinks about what class it is. So that could mean that this is a good thing to start labeling, because the neural network already knows what's here, has no problems with that, but has no clue what's, or at least if you slightly perturbate the input, decision switches. So there's, yeah, take a look at this paper. The paper is really clear.
I guess just then a follow-up question. Is it always the case that if something is unknown that it will flicker, like it will be on a decision boundary, or is it often in practice that you know it's never seen this object, but it's like I'm 100% certain it's a car? Yep,
that's a danger. So right. you can find the places where the algorithm is not clear, right? But you can also have the bad luck that the network is really sure that something is a specific object, but it's totally not. Yeah, that's always the problem. You can select where the network thinks, which the network thinks it's uncertain, but you might not have the completely wrong classes.
I have two questions.
Yeah.
First, can we get these lecture slides somehow? If
yeah.
now, is there a link so that we can share? Yeah.
If you go to the GitHub page, there's a link in the readme.
It's in the GitHub. So how come I missed it? That's not okay. Good. So that's that. I've tried also registering to the dataset mapillary.
Yeah.
And it says it's asking for a callback URL.
I didn't, or maybe I just filled in something randomly. I don't know anymore.
I filled something random. I'll try that one. Okay.
Yeah.
Third question for the audience. I will be repeating this today. Please turn on your video so we could see you, if you're able to. If you're not, it's okay. But if you are, good time to turn the video on. Yeah, that's it. Sorry.
Awesome. Yeah,
I have a question.
Yes.
How would leaving dropout layers improve, help us estimate the uncertainty?
Okay, so the thing is that, so the idea is as follows. You have a neural network, and if you don't have any dropout layers, you run inference, you get one answer. It's always the same. The idea is that if you leave dropout layers, then normally if you're doing dropouts, you're setting some weights to 0, right? Randomly. The idea is that you run inference 10 times or 100 times, leaving these random perturbations of your latent space in, which means that you will get some different answers on places where the neural network is not really sure, because you're kind of moving through hyperspace in your latent variables. But so because you do this 100 times, normally dropout is meant to make a neural network robust to perturbations in the image, and by actively perturbing, by actively changing the image, it will still give roughly the right answer. But if it's on a decision boundary, it might move it over. So then you know which things are kind of close to a decision boundary. Does that help?
Yeah, thank you.
Awesome. Yeah, and maybe then the other thing is to do test time augmentation of the data by changing the input slightly and looking at whether this changed the prediction. So, for example, if you would change the brightness of the image, and then you get a completely different prediction. I mean, the object in there doesn't change, but it does mean that the neural network is not that good at, or doesn't really know what's going on there in different conditions, which is of course not what you want, because if you're driving and the brightness outside changes, also known as it gets dark, you still want to know what's going on. Yeah, so that's it for uncertainty sampling. Another way, which is kind of doing the same thing, is doing called query by committee. So you train several models on an annotated subset of your data. So this is your committee of models. So let's say you train 3 neural networks, for example, or 5 neural networks. Then you can run predictions on your unlabeled data and label the data on which the committee disagrees. So let's say that you have pictures of cars and bikes, and you train 10 models, and 10 out of 10 models agree that one new picture is a picture of a car. Then apparently it's really clear that this is a picture of a car. As you already mentioned, by the way, it could be wrong. All the models could be wrong at the same time. But if then at some point 8 models think it is a car and 2 think it's a bike, then that might be a good indication that like either 8 models are wrong or 2 models are wrong, but apparently didn't really learn it or at the same time. So you send that data off to labeling. So you can also play around with this. So you can train the models on different subsets of the data. So you can maybe train a couple of models on the first half and a couple of models on the second half. So then if your data wasn't really well shuffled or has a different distribution, you will notice that then by then. And another really good approach in general is letting the committee consist of different types of models. So maybe you can have different neural network architectures. So they're both maybe good at different things, or you can have a classical computer vision predictor and a neural network. That also always helps with finding problems with either the classical approach is not able to handle or the neural network approach is not able to handle. And there's then also multiple ways to define disagreement. So you could say, oh, well, if there's any one disagreeing, then that's bad. Or if the predictions for how likely a car are different, then that's bad. So that is query by committee. And then the last thing here I want to talk about is having kind of a core set approach. So if you have a set of points with maybe 2 features, or maybe this is projected down way, can you define a set of samples which cover all the available unlabeled data? So if you have all these points, then if you select the blue points, then every other data point is only a certain distance away from each to be labeled blue point. So if you do this, if you would label the blue sets, you are kind of hoping that the other points are the same class as the other points. So this is also relatively easy to implement, which can be a good start. Then, of course, you don't know if the other unlabeled points are actually the same class, but at least you try to cover your entire data space a bit. So yeah, and then the last thing I wanted to talk about, which I personally really enjoy, is having an image search engine. So we all know the Google reverse image search, that if you are searching for a specific kind of image, you can frequently find it on Google. How does that work? Or wouldn't it be great if you had a problem with, for example, a caravan, or if you had a problem with a wheelchair, you could just take an image of a wheelchair and then search in your database to see if you have the same wheelchair. Or if you have, I don't know, the roads covered in snow, maybe you can find the same road covered in snow in more cases or on more different recording days. So you could, so normally if you have a problem, as I said, you can go on like a data gathering mission to hunt for this specific kind of data, but this takes a lot of time. So if you could use an existing model to go through your previously recorded data to find similar data, that would be great. So the idea is that if you have an image as input, you can maybe create an image descriptor. And this image descriptor, I don't have any classical examples, but one maybe easy way to build a descriptor is that you can say, okay, what brightness does your image have, or what kind of pre-labeled objects are there? So then you can manually build a descriptor. But what's way more interesting is to use a neural network or another machine learning model to create a feature vector. So if you have a neural network, then you have a specific output for your prediction, but you could also take the latent features in your neural network and say, okay, well, this is now my feature vector, and then you can try to find images which are similar or in terms of feature vector. And that means that apparently the neural network thinks that it has roughly the same content. So yeah, we will go over the downsides of this later. But yeah, the idea is here that you can have this similarity by activation. So, oh yeah, here, I already said you can have maybe your average brightness, you can have your average red, maybe you can have gradient magnitudes. And you can, for example, for your latent layer, you can maybe take your last layer before your final decision layer or something even deeper, whatever you want. And then the question is basically, if you have these two feature vectors for two images, can you have a distance metric or similarity function which says, okay, these two images are dissimilar? So in practice, there's maybe two which are used frequently. One is Euclidean distance, so that measures the distance between the magnitude and distance between the two vectors. So if you you can see my mouse, right? I hope. I've been pointing out stuff.
I saw it before, now I don't see it. Ah, yeah.
You can see it.
Yeah, we see
Okay, yeah. Sometimes I'm clicking on the zoom window to move it out of the way, and I think it might disappear. Anyways, the problems of modern technology. We can build self-driving cars, but we can't have see pointers. Yeah. Anyway, so in terms of Euclidean distance, if you have these 2 points, you can find the distance. Like this is the Euclidean distance, really the shortest distance between those 2 points. But you can also look, for example, at cosine similarity. So if you have clusters of points here and here, you could also say, okay, well, how big is this angle between the two vectors? This is mostly used for text data where the magnitude of features matters less, but really the kind of cluster they're in away from origin matters more. So this also works really well for images, for image data. Yeah. So yeah, if you put this all together, the thing you can also do today is first take a dataset of images, extract the features from each image using your neural network. Then let me go back here. Then store those features, and then whenever you have a new query image, you can extract the features from this query image, compare this query features to image features in your database, sort the results by relevancy, and display the results to the user. And this is also something someone already made a tutorial of, the complete guide of building image search engine using OpenCV. But I also made a Jupyter Notebook, which kind of uses a neural network. So these images are from this guy. So this is what if you run this, if you query or if you download a lot of data from Mapillary, this is roughly what you get. So if I have an input image of a highway, I will find other images of, yeah, I probably guess it's the same highway. There's a divider here. But yeah, you have loads of similar looking images. If you have an image here in the city, you have loads of similar images where you can also see, oh, it might even be the same bus or something. I don't know if there's a bus in the back, but you all have kind of narrower roads where there's some cars, where there's some trees on the sides. So if you ever had a problem with, I don't know, highways or inner city roads, you can easily find more of those. So yeah, in terms of the hands-on experimentation, I basically want to quickly say what I prepared for people. It is a bit of my idea was to build examples and let you all kind of experiment with it yourself, because I don't really know what kind of like level people have. I thought it would be weird to set specific challenges for everyone. So you can kind of figure out for yourself, what do I like to do today? What is a challenge I want to do? And then build that. So you can either look at uncertainty querying, or you can look at finding similar or finding images using some existing neural network with maybe rare classes, or you can look at building your own reverse image database. Yeah, so I already explained this, download these things, and then you can look at the following examples. Object-based selection, where you have a Jupyter notebook with an existing object detector in there. So you can use that to assess what objects are by default in data if you don't select any of it. You can also define some rarer objects like, I don't know, a dog or a bike, and try to see if the detector can find them. And maybe one challenge is, could you maybe find multiple neural networks and select data in which these two networks disagree, right? So that you can kind of do query by committee, where you download 4 different neural networks and see, hey, do the bounding boxes disagree in some way? Oh, then it might be interesting. Can you maybe see if the data you find does indeed like look interesting? And maybe if you're only having one neural network, maybe you can already find overlapping bounding boxes with different classes. So if you can find an example, so one maybe example you can find is a dog, which also looks like a sheep or also looks like a bear. Can you, like, does that make sense? Do you might maybe agree with the algorithm that this is indeed hard? What do these objects look like? That's one question. So then the other thing is having uncertainty based on latent features. So I downloaded a pre-trained object classification algorithm, VGG, which is trained on the ImageNet dataset. And the only thing I prepared is adding a Gaussian noise to the input of the image to create some uncertainty in the output. So we're just sprinkling a bit of noise on top. And if the network then starts disagreeing or with inputs, then that's not supposed to happen, right? Because there's only a bit of noise added. So you can look at the standard deviation in this latent space on images with noise to determine which images cause the most uncertainty when noise is added. And now the question is, can you maybe find other augmentations to this image and see if this causes other images to be selected? Or maybe another challenge is, can you use a more relevant neural network to find more interesting data? Or maybe can you download a neural network which normally has dropout layers, and can you add this dropout to get a, maybe you can even do like per pixel segmentation or per pixel uncertainty to see what kind of things are uncertain according to a semantic segmentation network. And then the last project is image similarity, reverse image search. So you get a pre-trained object classification algorithm, again, VGG, trained on the ImageNet dataset, and you can use these latent features to query similar images. So, maybe one other thing is that for these features, you never really know what they select. Or sometimes people ask me, but what does a feature mean? So one thing I also added is add a visualization of the saliency, so you can try to reason what parts of an image trigger what features. So one thing you can do is try to figure out what distance metrics work. Maybe you can query. One thing I also like, if you have this mapillary or if you have your own data set, maybe you can query an image from one specific city and find similar images in a different city. And another thing you can try is, can you find specific latent features you really like, which you want to find similar images for? And a new idea is, can you find unindexed images which have a large distance to already existing images to ensure that you have a great coverage of data? So then you basically index a certain set of images, and then you also index another set of images, and you look, okay, is there any like image which has a really, really large distance to the normal data? So for example, when I did that here in with this data from Mapillary, I found an image of the Oktoberfest, which looks really weird compared to the normal empty streets of Munich. But yeah, those are some ideas I had. You can also just.
Maybe it's a good time to ask. So sorry that it's interrupting, but
That's the end of my presentation.
How robust are autonomous driving algorithms, especially in cases like a market? Just so.
Yeah, I mean, you have to collect data to verify that everything is working right. So your image detector and your pedestrian detector has to work. So
are there examples that these cars work in these environments, or nobody tries it yet?
Well, so right now, most of the cars which are really totally driverless are driving in like relatively empty white environments. So the bigger problem also with markets is not really it's not really the detection of the people. Like you can generally detect them really well. The problem is more the prediction of what they're going to do. So people, it's always harder for you also to drive in those environments because people are moving all over the place without paying attention. So that makes it harder.
And a person also knows that if you move the car forward, that people will move.
Yep.
And I don't know if the algorithm knows this or if we wanted to know it.
Yeah. There's always like a tiny dance in between the people taking right of way, giving right of way, and this dance is really hard to learn. Also, especially because I think that's something which Drive AI try to solve. They basically put on cars remarks with, okay, I am waiting for you to pass. So that's the alternative for you move, which you normally do if you're driving a car.
Oktoberfest simulator for AV. Yep.
Yeah, I don't know. I think in Oktoberfest, whenever it's September and or Oktoberfest here in Munich, there's always drunk people walking in their bike lane, which I hate because I like cycling really fast. But they're just suddenly walking into the bike lane, and that's always hard to deal with. But yeah, for self-driving cars, you then have to maybe recognize, is this person wearing lederhosen? If so, they might be drunk.
This is great. I have like a high level question about just like autonomous vehicle, like how it's been going and everything. So it seems like most of this talk is, hey, we don't know something, so let's train an object detector for it. And then you imagine, that poor guy like cataloging all of the stop signs probably in the world. I mean, it's a long, it's a huge task. And so, this long tail is combinatorially large. Like, is that the approach? Is just to shove it, into a neural net one-to-one, like type of stop sign into, neural net? And I'm just wondering how scalable is this?
Yeah.
Is there a better way of doing it?
The scalability is basically the next challenge, right? Because right now, many companies are driving in Las Vegas, many companies are driving in the Bay Area, many companies are driving in Pittsburgh, for example. But eventually, what you want to do is deploy in every American city, every European city, more cities. So right now, the question is how much extra data. It's this is maybe kind of a domain transfer task, right? If you can drive well in Pittsburgh, how much extra data do you need to also drive in New York? If you can drive in Pittsburgh and New York, how much extra data do you need to drive in Munich? If you can drive in these three cities, how much data do you need to go to the next city? So I think there will always be a bit of an extra need for data because every city has different kinds of people, different behaviors, which are normal. But the overall challenge is really reducing the amount of data you need and selecting the right data. Like if you every city you get would just randomly select some frames to learn it, that's maybe not the right approach, right? Because if you go to a new city, your car already knows what a car looks like, what a pedestrian looks like, but maybe it's really confused about some specific stop signs in that area. And maybe it's really confused about some behaviors which are maybe normal in New York, or maybe some objects which are, maybe New York has hot dog stands, Pittsburgh probably doesn't have hot dog stands. I don't know if that's a really clear example, but if you're going to stop because you want every hot extent to pass, that's not a good behavior. So then, of course, you have to label a few of those. The question is really how much of everything do you need to label? It's all about, maybe also in this case, it's about two things. One is, can you scale the algorithm up to drive in the city? And the other question is, can you prove that your algorithm can safely drive in the city? How much data do you need for that? Do you need to drive for a certain amount of hours there? Do you need to, or can you build some safety report where you say, okay, well, we collected this amount of data, and we see that we had zero false negatives. So we detected everything in this area. So now we can drive. Proving that it's safe and that it's secure and scaling to new areas is the next big task.
Is there some like sophisticated like backend for parsing through like semantic categories of the scene?
I have a before this.
Yeah.
Sorry, guys, I'm interrupting. Just some people might want to start working on the code and stuff.
Okay, yeah, we could do that.
I will do the questions for sure, Arthur. I'm not like I just want people to start working, and at the same time, because it'll be boring just to watch people pressing keys, so we could talk about questions. So first, let me share my screen, Roland. I think it's working on the Colab.
Awesome.
So anybody who wants, just go to Colab Research, Google.com. You press File, Open Notebook, and here you have Upload, and you upload the relevant IPYNB file, the relevant Jupyter Notebook file, and it works. What didn't work for me was the mapillary. I couldn't register a key. So if I tried, it didn't work no matter what I did. So like I do like some fake domain, something here, and I do read, register, and it does this.
So it's basically not giving you a key. In that case, just download the 1,000 images I uploaded. So then everyone is just working with a smaller data set, which is fine. Because working, then just try to get a key later. Or try to find your own interesting data set, which is probably more fun anyways, later.
So a question here, because in Colab you can't run Docker. It runs without a Docker. It just has all the dependencies.
Perfect.
Where can we find that data that you mentioned, 1,000 images?
If you if you open the slides, which you are linked in the GitHub, there is this drive.google link here at the bottom.
11?
Here at the bottom, on this slide.
I'm on my screen. I'm sorry, I'm not just the right bottom.
Let me stop sharing. Then I can. Here I can see. No, go 3 slides up.
3 slides up. 1, 2, 3. Here.
One more.
Here.
Download this data. So this is drive.google.com.
So whoever's going to do this on here, I think there is a way to do this on Colab. I don't remember now. You guys can see my screen, right? Or no?
I can.
Yeah, you can. Okay. So Colab connect drive. I don't remember the command ever, but this will be easy. As you can see, I've already searched for how to do these things. Oh, yeah, good. So we got to do this. So let's say I'm going to work now with object-based selection. I'm going to add this here. And blah, blah, blah. We don't need this. We just need to download. So I'm going to take this thing. Oh, there we go. Yeah, that's what I want. Okay, now it's asking for authorization, and I need to authorize, and then
you have many accounts, man.
My life sucks. I know. Yeah. So we have it, and now it's here, and now it gives me a connection to my drive, and I can download stuff. But doing all this, I thought, okay, it'll be just faster to download and upload it directly to the Colab thing. So you go here. Small zip. Is it gonna use small zip, or I need to use what's inside of the small
You
zip?
need to point to the path.
The path. Okay.
And it should download relatively quickly because it's only 100 megabytes. They're all JPEGs. Also, if you go back to your object-based selection, you are downloading at some point a model. Here, this ResNet model. Yeah, so that succeeded. But is it now like in your collab?
It should be. It says index out of range, but it did reach this point. So
So then the question is, if you click on the left of your screen, can you see your ResNet 50 Cocoa Best v2? Yeah. So that's what you need to point to, but I don't know how you. Oh, here, because it does os.path join execution path, but maybe that should be just only the.
No, this is good here.
No, so maybe you need to remove os path join execution path.
This one.
Yeah. So. So that needs to point towards where this model is, which managed to load. So that's good.
V2. Let's just copy this name.
Yeah.
It says this index out of bounds inbound nodes. It does have the shape, right? It has it recognizes the shape of the model for sure.
Yeah.
Something else is bothering it. Maybe because I don't have
What they say, is it possible that this is intended behavior? It's more likely an omission.
No, it shouldn't be like this. Why?
What TensorFlow version do you actually have there?
It says in the beginning somewhere here. Where does it say it?
It says 2.5, I think.
2.5.
Yeah.
Is it good, or do we need another version?
Wait a second.
In the meantime, everybody, you can just start opening these things either on your Jupyter or on Colab. We're gonna fix the Colab. In the object-based selection, you'll need to pip install image AI. So you just press exclamation mark, and this gives you like a bash command basically. And now you do pip3 install image AI, and you'll have that package installed, and then you can start doing all the imports that we can see below here. We just need the image AI for the object detection.
Wait, you said you had TensorFlow 2.5?
Yeah.
But I'm like using the Docker container's latest GPU Jupyter, and it has 2.4.
It's Colab, but I always have the latest, but we can downgrade it if we need.
They have not just the latest, they have newer than latest.
Yeah. If we need a 2.4, we can.
Yeah, also, if this is not working, then just try a different notebook and see if that works, right?
Okay. The other notebooks, they do work. I did run some of them.
Awesome.
I think I did. Which one I did? This one I ran up to this point. It builds the model basically, but I didn't have the images, so I couldn't do the whole thing. Now I want to upload the images. So how do we upload a file? Colab upload. So if we're gonna go here, file upload.
Yeah, I see that they already released 2.5 already a while ago. So I guess I'm just out of date nowadays.
No worries, no worries.
Gotta keep up with machine learning.
Wait.
That's always good, you know. You're learning something new on a meetup like this.
True.
They already have a new TensorFlow for 2 months.
Mount Drive. No, I don't remember any time. I don't remember how the commands for uploading import data into Google.
Yeah, that's why I'm normally just setting up an Amazon instance or something, like full control of whatever you're doing.
Here we go.
Actually, I guess you can just upload the data on Drive. Then
No, it
use
should work like this. That's it. Oh, there we go. Now it should ask me which file I want to upload. There we go. Undefined. Oh my goodness.
What is really good is that we have 19 people who can debug loading a file.
For sure. Anybody who, by the way, if you did manage to run your collab, just share your screen and show us. But this should be working. What I did now, that's the way to do it. No, I don't want to mount the drive. I want to upload a file. This is very peculiar. This works.
In the meantime, I'll just keep making lame jokes, such as nowadays we can build self-driving cars, but we can't load a file.
We had a question. I think Arthur asked a question which I interrupted, so it's a good time. Maybe Arthur, if you want to ask it again. I wanted also to mention before I sent a link to the YouTube with our new scenes talk, which talked also about transfer models from different scenes, different places in the world. I think Germany, Singapore was examples there, United States. I don't remember exactly where in the talk, but if I remember correctly, it was in that talk. Yeah. I'm gonna stop my share in the meantime while I'm searching.
Yeah, and then also nobody can see anymore that we're having problems with loading files.
Exactly.
And that being live streamed on YouTube.
Yeah, I'm like, I know what I'm doing. I know what I'm doing.
Yeah, live coding is really terrible. I really have so much respect for like Twitch streamers who are doing this on a daily basis.
Yeah.
Anyways, you were talking about the differences in terms of Singapore and other countries. That's actually a major problem, right? So I think that Waymo has a challenge. Waymo has data sets both in I'm going to say New York and the Bay Area, but I'm not sure. But one thing they are hosting and paying good money for solving is doing this transfer learning, where you are training a model. Let's see, how do they call it? Here, domain adaptation challenge. You're training a model on one data set, and then you're maybe seeing some data from another location, but can you still detect all the objects there? I forgot how much money they are paying for this. Yeah, here, first place, $15,000. That sounds like a pretty good thing to reach if you can solve it. But yeah, it is a problem that there is a difference between areas, and if you're training a neural network to learn one place, it's not necessarily learning the other place, which is a bit counterintuitive, because if I come into Singapore, I think, oh wow, the cars here are so different, but I still know those are cars. I'm never thinking, oh wow, the drivable area here moves. But yeah, it's a big challenge.
So I guess my question was that you can imagine, like, each scenario you have an object detector and it's going to tell you what to do, but that just doesn't seem scalable, like I was saying. And so, when you think about transferring to different cities, you kind of have to think about, how does it scale? How does your data structure, like, what's the organization of your system? And so I was wondering if there's this like sophisticated backend kind of, you start with a semantic category, like maybe junction, and then you say, okay, look to the right, you'll see a stop sign, and then, oh no, it's a specific type of stop sign. It's yellow, and then so you break into these subcategories. And I was wondering if there's something like that. Is that what people are doing, or are they doing more sophisticated, like latent, meta learning stuff? I don't know.
Well, so what part of the system are you talking about? Is it like the computer vision or the object detection, or is it this already like the what is your eventual driving behavior?
The system I'm describing will break each scenario down into different neural nets. It's kind of like it's not everything in one. I mean, I don't even know if that's possible in the first place.
Yeah, so you basically say, oh, we have a specific neural network for driving over an intersection, and we have a specific neural network for driving over a straight road, and a specific neural network for a roundabout, or...
Yeah, is that the case, or is it more towards monolithic stuff? Like, what's the back end look like?
Yeah, it's more monolithic stuff. So you have like one. I mean, I can also give this presentation at some point here, but I think it's already a bit more common that people are talking about the different architectures you have, but very often people are splitting it into the detection. So you say, okay, well, I'm seeing these objects, and then the prediction, like what are all the objects going to do, and then you have the driving policy, which is then receiving, oh, these are the objects I'm seeing, and this is where I am on the map, and this is where the objects are going, and then you try to find a path through this environment. And the big open question here, I think, is: do you have a neural network which works in all the environments and all the circumstances, or will you have a I will share it in the meantime. I can see some things again. There you go. So the question is more, will you have one neural network and one car which is specific, or which is working everywhere in the world? Or will you have still teams who are adapting the driving policy, etc., for all the different cities you're in? Or maybe will there be a neural network for day and one for the night or something? Could also be an option. So because in general, learning more different environments requires a bigger neural network and requires more data, and is less specific than having a neural network for just one task. But then how many tasks are you going to split it in? So I think that splitting it into two tiny pieces is a bad idea, because then you need to collect data for all these things, and neural networks will benefit from the overall picture of the whole world. But yeah, maybe at some point you want to split. I don't know.
Yeah, I'm just raising this because let's say the long tail is super long, right? And there's so many scenarios. You have a guy in a gorilla suit pushing a stroller, and
Halloween, fun
right,
moment.
Right. There you go. You're Halloween. You're in Oktoberfest. So you have to balance your data set now. You have to sample it to an extent that it'd be representative of, that it'd actually know what to do. Isn't there something like catastrophic forgetting with neural nets that eventually just runs out of the ability to do anything?
Yeah, I think that here there's maybe two things. One is my point is a bit that you want to be able to react quickly on those situations, because, for example, let's now maybe Oktoberfest and Halloween are I guess reasonable examples. But if it's Halloween, suddenly all the people are behaving differently in Munich, also known as they are drunk and dressed differently. And but if you have a self-driving car system, this is the moment where you still want to transport the most people. So your car has to keep working and quickly learn and adapt. The other thing is the amount of edge cases is kind of infinite. So at some point, your car also has to have the ability to say, okay, I don't know what's going on, because if I'm driving, sometimes I don't know what's going on, and I park my car next to the road, and I'm safe. So at some point, your vehicle has to be able to say, okay, I have no clue what this is. I'm not driving here. I'm not going there. Or I'm taking a different route because I have no clue what's going on there. So that is something which you should be able to detect and act on. And then the question is, how often will this happen? Does it mean that if there's, there's also something which I always think is interesting. There's a big difference in what humans have problems with and what machines have problems with. And it's very confusing for people. So for example, the example Andre Kapati showed us with his lights and this, for example, if you have glare of the sun in your eyes, as a human, you kind of like move your eyes until you can see traffic light. So it's very clear to me as a machine learning engineer that a self-driving car could have problems if there's glare with detecting whether it's green or red. So if there's a self-driving car in front of me, I'm patient and I will not honk immediately. Whenever I was driving a self-driving car, and this was the case, it takes 1 or 2 seconds more to recognize, okay, it's really clearly green now. You want to be sure. Cars behind you are really impatient because they think you're an idiot. Because you as a human are an idiot if you wait for 3 seconds when it's green. But a neural network will make a different mistake. Same for that, maybe a neural network can think someone is crossing, whereas this thing or this someone could actually maybe be a moving bush or something because it doesn't really know what it is. It's moving a bit. Yeah, as a human, you just see, oh, it's a bush, but it's a completely different mistake. But as a human, you're not anticipating that a car in front of you will brake because there's literally no one there. So that also makes it a bit harder. Did you make it? Oh yes, we got the images.
Yeah. So yeah, but the other stuff is not working now. So first I used my drive. I used this didn't work well. It took a long time to upload. So you can just go with google.colab import drive.mount. Then you tell it where you want it to mount on Colab. I told it content drive. And then when you need to connect the zip file to your own drive, put it in your own drive, and then you can download it from your own drive. That worked. The VGG model loaded. Okay. Now this part didn't do anything.
Okay, so you have to point to the right.
That's the folder, yeah. It's here.
What does it say with? I'm dumb. Can you remove the -1000 there from the end in 23? Yeah.
This thing, yeah.
Yeah. Try this again.
Okay, looks
yeah
better.
Okay, because I thought, oh, let's index everything except for the last 1000, which can then be like a fun test set.
But it's super slow. But let's see how I can make
no
it
this is actually fine. Or yeah, if you can have a GPU, that will be better.
I can and I will.
Also, the code is more programmed towards making it easy to understand the code rather than making it fast. Because otherwise you get like weird data pipelines. And
yeah,
now I hope that it's really clear, like, oh, I'm taking one file and I'm getting one feature and storing that in a simple data store. And yeah.
Yeah, right now it should be easy for us. That's the good thing with those notebooks. Once it's working once, it'll work many times easily. So that's it. That's now inflating everything. Then we're gonna run the model. Folder the features. Anybody else made it work for them? Does it work for anybody, or I'm just the only one trying is me?
Is anyone even interested in trying this?
If you have tried it, let us know. Share your screen with us.
So what I think it is, Peter, is that there were like over 100 people who said they want to come to the meetup, but they figured out the code already before the meetup, so they don't have to join anymore.
I'll tell you the secret. 80% of the people watch the YouTube recordings, and 20% they come to the talks themselves.
Yeah. So we can say hello to everyone who's still watching YouTube.
Exactly. This will be an amount actually. Yeah. So it's taking some. Is everybody watching me code? This is what happening really?
Maybe one thing which is also good is if you have this timer, you can stop it at any moment and then go to the next thing. And
there we go.
Yeah, so that's all fine.
That's okay.
So you go to the next cell. Yeah, here. So then you can build your nearest neighbors metrics.
It worked. And now data selection.
Yeah, so this is your query image, and then you're finding these similar images. So
Okay.
the top is your query. The smaller images are your result. So here you're querying for like a person on a bike, and you find a motorcycle. I think that's a great result because motorcycles are pretty rare.
And here, like, what is the query here? You'd say it's like a freeway.
It's like a freeway, and we're finding more examples of freeways. Here we are querying like a blue weird bus, and we're finding more buses.
Nice.
Oh, so maybe that's another thing which I didn't really explain very well, I think, during the presentation. But when you are building these kind of algorithms, the fun thing is also that so normally if you're doing machine learning, like you want to have a high recall and precision, right? You want every example to be like perfect. The fun thing here is that it takes me so much time to find a sample of a bus that it's faster for me to query like a part of a bus and then find 4 samples. It doesn't matter that 3 out of 4 are not a bus because I found another sample I was really interested in. And so whenever you think, oh, my algorithm is not working because it could only find. So for example, in this data set, I queried my mapillary for a bit longer. So I have 50,000 frames. If I query for like a child on a bike, I only find maybe 5 examples. That's cool because before I had 0 children on bikes in my data set, and now I have 5. So that way you can bootstrap your algorithm. So Andrej Karpathy is always saying that they started off with having maybe 50% recall on a data set, so really low. Then they started collecting more data in this way, kind of like tuning the data engine, getting more like a slightly larger amount of samples, and then using that algorithm improvement again to find some more examples. And that way you can find more and more samples. So if you think, oh man, I query for an image with a bike and I can only find 1 sample with a bike and people, that's pretty good. That's nice. You get some more samples. Oh yeah, this is the saliency. So here the question is, what is your neural network looking at? So you have your features, right? And you don't really know what a feature is, but what you can do is look what parts of the image really activated this feature. So you can see that there's apparently one feature in VGG which is kind of looking at the wheel, one thing which is more looking at the road, some are more looking at the trees. So maybe you can, as a challenge, try to find some interesting features and seeing if you can make those features more important for your nearest neighbors and find some with maybe specific types of trees, or maybe you can find some with specific kind of objects. So overall, I would normally, it's always fun to see what neural networks are latching onto. Also, this is, I don't know, are there already explainable AI topics discussed, Peter, or not?
Yes, of course, we had many. You know what? Let's see which one we had for explainable.
Because this is also always something.
So what the adversarial attacks, you could say that were like explainable AI when you're trying to exploit the model and show where it's lacking. And we had just the last one is adversarial attacks. We didn't have black box explainable AI still, no.
Yeah, so that's something which I always think is interesting, that how do you prove that your car is safe on the road? Well, part of it is probably by saying, well, if my neural network is making the decision about where a car is or not by actually being activated by this car on the road and not by some features around it. So it's also possible that, for example, one problem I had at some point was that I collected a lot of data at one point and there were always people walking the road. So whenever at some point there was a pandemic, there were not that many people on the road anymore, and the algorithm was like, I know this place, there's loads of people everywhere, and that's bad. That's not what you want. Yeah, but so that's the problem, right, with neural networks. You never know what they learn, or with machine learning in general, you never know what they learn. So you can use saliency as a way to see if everything is going right.
We'll direct people. We did have a talk putting visual recognition in context exactly about this thing, where you want it's not only what's appearing but also what is around it, and try to mitigate both. So like how can I find a nice example here? I'm not good with finding things right on the spot, but let's see on our chapters. Maybe we'll have it somewhere here. Yeah, so in these examples, the question was, if we take just a part of the image, will the network be able to recognize what's in this part if it doesn't see the context, or if it does see the context? So you could look at it as explainability in a way in which does it need the context to explain what it's seeing or not, and how will a human also behave with this thing? I'm gonna share the talk here. Where's my Zoom? Chat. There we go. Shared. So you guys have it. Oh. Yeah, this is not interesting anymore. So back to here. So we have this thing. Did anybody else try running image similarity?
Peter, could you just show me again how you connected your drive?
Like this?
Yeah, exactly this one I have, and then I just unzip it directly. Okay.
Yeah.
All right.
And then you gotta connect the folder here and the bill of dataset database with all images.
Peter, can you share this?
I'm share it in what way?
I mean, like.
Like type. Okay, go ahead. There you go. So that's the lines, and then you use this. Roland, you want to take the next notebook and share it on your screen on Colab for the people?
I don't
would
have
like to have a break.
Also,
you just go online. You just go Colab this link.
What I can do is, instead of showing it on Colab, is I can take the screen and then show the uncertainty thing. Here, let me do that.
Go ahead.
So then it won't be in Colab, but the ID is the same. You know, can't be that difficult, huh?
Sometimes it is, but let's see.
Yeah, I know. No, so the thing I'm doing with the network uncertainty is that everyone can see my screen, by the way. I'm showing, otherwise give me screen.
Now we can see.
Very good. Yeah, so the idea is that I basically do the same as the previous notebook, but then I take, and I again take a VGC16 network with ImageNet layers. What I do here is I change the model to add Gaussian noise on top. So just tiny amount of Gaussian noise. In my case, my folder is still this. Remember to remove the last 1,000 again, because I always try to keep a holdout data set so you can validate things. I have the function get features from image, which just loads an image from your image path and then pre-process the input and predicts. So that way you get features and image. And what I do is, instead of doing this once, I do this 10 times. So you can also play around and try to do it try to do it 5 times or 100 times, whatever. So yeah, after I indexed, I don't know, 10,000 frames, it's interesting to look at. So the way I basically, what I basically do is I take the standard deviation of the image, and then I look at what is what gives you the most uncertainty. So what you can see is that, for example, here's a weird 360-degree helmet shot. There's a really weird case where there's a blocking thing with a car. That's I would say that's kind of weird. That's pretty interesting to annotate. This is a street corner, but then with snow, which I would say is normally pretty interesting to annotate. Here there's a woman on a bike standing on a bike path, so that's also pretty interesting to annotate. So you can see that that you have some weird uncertain images. What's also interesting is doing the reverse, where you say, okay, what is this algorithm most certain about, or what is it? What things should you maybe not annotate? And in this case, you can see that you get loads of images of sky, trees, whatever, which are always kind of giving the same activation in the neural network. So I think that's interesting. What you can do if you see this is also maybe try to add other augmentations, or maybe you can use a more relevant neural network, because maybe the trees are really interesting to see for you. Those are the things. And the last thing is maybe you can add noise to the latent features to see if the final predictions change, or use other layers in networks that you get a bit deeper. But yeah, that's basically the idea. By the way, do you see my whole screen or not?
We see the whole screen.
Very good. Any questions, by the way, on the uncertainty? I'll take that as a no.
Did anybody run something? If you could show us, it'll be nice if you did run anything. People from the audience. No? I want to see stuff. What's going on here? Really?
Let me set up my collab.
Maybe the last thing which is interesting, I'll walk you through this, and then also at some point, just send me a message on LinkedIn or something if you have any questions. But the last thing which is pretty interesting, I think, is that you can load a model from Image AI. So Image AI is pretty easy to use. You can have different object detection models with different, where they already have different pre-trained models which you can download. Don't see them here, but I basically downloaded a ResNet model. And one thing which is interesting is looking, okay, if you are not doing anything with the data, what kind of objects do you see then? So I ran this for, I think, 1,000 images or something. And I see 4,000 cars, 700 trucks, 600 people, 307 bikes. Remember the bikes? I hate bikes in my data set. Buses are already rarer. So that's why it's so good that if we have a query with a bus, we find a similar image with a bus, because they are pretty rare. And the motorcycles and trains are really rare. And even this 34, I suspect that this is a lot of false positives. But yeah, so then you can see kind of how important the need for active data selection is. And one thing I think is fun to do is define a couple of rare classes, like, for example, bicycle or motorcycle. Wait, let me actually do that right now. There we go. So then you can go through the images and then try to find images which have a predicted bike or motorcycle in them. And then the same for dogs, horses, cows, sheep, bears, birds. This model, so here you can see that we can already find here a person on a bike, which is detected, 2 times detected a bike and a motorcycle. But yeah, so it's also good to note that not everything you find is actually an example of the case, which makes it even more important to annotate the things which you do find. And also, if you get to the rarer classes, what's fun is that this COCO dataset is trained on all kinds of objects. So you can also if you want, try to find cases where the neural network thinks that there is a broccoli or a teddy bear or something in the image, because then you know it's wrong, and you can try to see if something looks like a teddy bear. One funny anecdote, by the way, I always show this neural network to children whenever there's a moment to teach kids about self-driving cars. One thing which I at some point saw was that if you are wearing like a gray vest and you're like hunching a bit over, you can be detected as an elephant. It's always fun to try to fool these algorithms yourself.
Green jacket and you lean over, then it.
If you have a gray jacket, if the neural network tries to find like gray patterns, right, to detect an elephant. If you then like lean a bit over, look like you have two legs. It's really fun to try to fool a neural network into seeing something. It's also fun to let kids do it because they have no clue how these computers work. So I told a kid, oh, try to look like a dog. And he like went, oof, oof, oof. Because that's the feature which we most associate with a dog, apparently. But yeah, as I said, normally if you have a normal distribution of bikes, it's pretty rare to find them if you randomly select data. But if you then use something like this, you at least find them. So you can send them to a collection to be collected. As I said before, the problem with this approach is that you only find cases where the neural network can already detect them. And you don't find the cases in which the neural network has really no clue how they look like. So if you have something which is completely out of your normal distribution, the neural network will never find it. And you can only find out in practice. So one example, for example, which I really liked is that imagine that you're driving through the city and you have traffic cones. Normally, traffic cones are orange, but you also have some cases where traffic cones are green. But you're like, as a machine learning engineer, it never occurs to you that a traffic cone can be another color than orange. But as a human, you just see a traffic cone. But yeah, so if you have a traffic cone detector and you're trying to find data with traffic cones, you will probably find the orange ones, because that's the most common class. So this is not a good approach to finding green cones. But what you can do is, if you do have examples where your algorithm failed because your car took the wrong turn or tried to drive into a green cone, you can use the image similarity query to find other examples of green cones. So yeah.
I think I would love to see if anybody ran the code and stuff happened for them. I would really like to see it. Otherwise, Roland, maybe we could could finish a bit earlier. I think we covered everything.
I think so too. I'm kind of out of funny stories, so I'm if you have things like, if something is not working with a notebook, just make an issue, or if you improve something and it's way better, make a pull request, or add me on LinkedIn. That's kind of where you can find me. That's it then.
So thank you everybody for joining. Roland, thank you for raising the hand here and having this happen. I know I had fun, and I think people also have a lot of benefit from it. I saw like 9 stars already just on this Git profile, this Git project of yours. Is it what's going on here? Why don't I see my Zoom? I hope everybody can see me still. I don't see you. I think I need to wrap it up. I don't see.
I can still see you. I can still see you. But yeah, okay. There's apparently indeed already 9 people who started and are.
So I think people are getting benefit from it. I think that thing you showed us, where you can look for the rare classes and see examples, extremely important, extremely relevant, and cute also at the same time. We have a question here. Can you give insights about using public dataset pre-trained weights and annotations for commercial purpose? Is there any restrictions?
All the stuff here is all easy to, is all open, all for commercial use, etc., etc. Yeah. By the way, if people are commercially interested in this, all the stuff we have at Anatel is working way better and it's instant instead of running a notebook for a long time. So if you have a need for building data sets, reach out to me because then we can hook you up with a good data set. And also have have everything there included, like all the querying. In terms of public data sets, there's some really nice ones which are also for commercial use. So there is the Panda set, which is for commercial use, A2D2, which is for commercial use, Mapillary you can use for commercial use, I believe, as well. And Shumik is also right with would love it if they were implemented on Colab. Peter, I think you can share Colab notebooks as well, right? Or does it then?
It's the same. It's sharing. Exactly the same.
If you can add it to README or something, that would be great. Then people can just click.
I think also it's actually you just do drive.mount. And that's it, and you can work for the full thing on Colab. It's no issue there. So, so if anybody wants to,
sure would be nice if you could share, because I'm trying to, but the model raises an issue if I'm trying to load it, so I'm not sure.
This is the screen. Which Colab, which notebook were you sharing?
No, the other one is the object-based.
Yeah, I will take a look at that because I think I'm using an older version of TensorFlow. I made this 3 months ago, and in the meantime, a new version released, and I didn't really think of that.
Okay. So that one, Roland, you gotta check first because we tried running it on mine and it didn't work.
Yeah, it's also my mistake because I assumed, I make it in Docker, so it will be the same for everyone. But I didn't do a complete from scratch rebuild for my Docker containers. So
I think we're talking about this one, which also for me crashed here. Yeah,
it's the same one. Exactly.
Yeah. So that's the problem.
There's some layer issue.
Yep. I will try to fix it.
I think if we install on the Colab TensorFlow 2.4, this would work. So you just need to downgrade the TensorFlow on the Colab device, and that's it. So coming back to the summary, thank you everybody for joining. This will be recorded on YouTube. We have a lot of upcoming sessions. Many of them are about autonomous driving, by the way, and some of them are also about research that is with open source. It's all on the meetup page. I will say bye and a good evening for everybody, or a good day, depends where you are. And until the next time.
All right, thanks a lot.
Bye-bye.
A lot of fun.
Thanks, guys.
Yo.
Bye-bye.